This chapter is about introduction of deep learning. So here in this chapter, instead of covering all different kinds of deep learning methods, I'm going to talk about the differences between traditional neural net and deep learning. More focus on some advantage of using deep learning over a neural net. So that is the basic focus of this chapter. This slide shows the popularity of machine learning algorithms over time. So in the beginning, like 1990, 1960 something, perceptron was proposed. This is actually the first machine learning method. But because of the Minsky's paper, the perceptron method was linear classifier. So actually people lost interest in perceptron. So since this year, all the way to late 1986, I guess, nobody care about the neural net AI in general. So this area is called dark age of AI. So around 1986, we have multi-layer perceptron, and the backpropagation was proposed this year. And now the neural net gains popularity. Okay, and around the same year, we have a new method called decision tree was also proposed here. So neural net gains popularity, and decision tree was pretty popular. Okay, then late 1990s, a new method called SVM was proposed. Okay, so this one becomes very popular, very powerful. Okay, so since the introduction of SVM, actually neural net lose popularity like this. Okay. And also at about the same time, we have a new method of ensemble method, random forest and ADA boost. So this SPM and this ensemble method were very popular, okay, quite competitive. So neural net loses popularity, okay, gradually. And then around 2006, this is the year of deep learning. You have new papers. A breakthrough in deep learning, and deep learning was proposed this year, and then all of a sudden this deep learning, actually neural net, gains popularity, and actually it takes off. Okay, it goes like skyrockets. Okay, so that's what happens these days, and this this shows the popularity of deep learning. So these days, deep learning is so popular, and everyone is talking about the deep learning. Here it is the Google trend, and around 2000, around this year, actually this is the search keyword. The search keyword machine learning actually is more popular than AI in general, so it's quite interesting. Okay, so many people are more interested in machine learning than in AI in general. Okay, so this also shows the popularity of machine learning. So what is deep learning? We have learned neural net before. So what is deep learning? Oh, actually, deep learning is a kind of neural net. So if you explain deep learning with respect to network structure, you can say deep learning is a neural net with many hidden layers. So deep learning is a neural net with many hidden layers, then that is deep learning. Okay. So in terms of network-wise, the difference between deep learning and neural net is deep learning has many layers. Okay, that's the only difference in terms of the network structure. But of course, the training method is different in deep learning and neural net. So this picture shows this is perceptron. In perceptron, there is no hidden layer. This is multi-layer perceptron. We have a hidden layer here, and deep learning actually has many hidden layers. Okay, that's the only difference in network-wise. So I said the difference between deep learning and neural net is deep learning has many hidden layers, and neural net has just a few hidden layers in terms of network structure. So deep learning has many hidden layers. Let's call it deep network. And neural net has just a few hidden layers. Let's call it shallow network. So the question now is deep network better than shallow network? Okay. So network with many hidden layers is better than network with just a few layers. Is it better or not? So that is the question. So general consensus in this issue is the following. Okay. So the first one is suppose we have a two network. Okay. The first one is deep network, like deep learning, and the second network is just a neural net with shallow network. And suppose these both networks try to solve the same problem. Okay, you're gonna solve the same problem using both of these. Okay, suppose network try to solve the same problem. Then the thing is, in shallow network, the traditional neural net actually need more neurons than the deep network. So they both network solve the same problem, but actually shallow network need more parameters, more neurons to solve the problem than deep network. That's the first consensus. Okay. So by constructing deep layer structure, actually you can save the number of parameters in the network. That's the first advantage of deep network. So again, we have two network structure: deep network, shallow network, and assume both networks solve same problem. Then in deep network, actually we have less number of parameters than shallow network. So that is the first advantage of using deep network. Okay. And if you look at this picture here, it shows the effect of depths of hidden layers. So this is number of hidden layers. So as the number of hidden layer grows here, actually the accuracy grows like this. Okay, so that shows the advantage of adding hidden layers in deep network. The second advantage of deep network over shallow network is in deep network, the feature learning is possible. In feature learning, so in deep network, we have many layers. So feature learning means in the lower level layer, it reads input and extract some important features automatically. And then by using these features in the next higher level layer, it extracts another set of important, more higher level features automatically, and you keep going. So near the top level layer, we have very abstract, very higher level features of original data. So that is feature learning, and this is very important characteristic of deep network. So that is the second advantage of deep network. So overall, deep network has some advantages over shallow network. So that's why this deep network is more, I would say, powerful than shallow network. But as you can see here, down here, so that is not always is true. Okay, it's in some other cases in this paper in 2016. So deep network is not always better than shallow one. So in this case, the wide shallow residual network, it has only 16 layers, but it outperforms deep ones, which has 150 layers. So generally speaking, a deep network is better than shallow one, but not always true. So we need more study on this issue. So deep learning is neural net with many hidden layers. But we already have neural net with many layers before. Okay, so we have a multi-layer neural net with backpropagation algorithm, and this has been around for actually many decades now. So you may wonder then what's actually new in deep learning? What has changed in deep learning over neural net? So I'm going to talk about this issue, what's actually new in deep learning in next slide. And here for now, I'm going to focus more on the problems of backpropagation algorithm in traditional neural net. So we're going to talk about these two issues in this chapter. Okay, these are a little minor. So the first one is vanishing gradient, and second one is actually feature learning. So second one is, I'm going to say this is an advantage of deep learning, and I'm going to say this is the problems of backpropagation algorithm. Okay. So vanishing gradient problem is when you have many layers in traditional neural net. There are some changes in higher level layers near the top level layer, but as you go down near the bottom layer, actually nothing happens because the gradient value in lower level is almost zero. Okay. So because the gradient is almost zero, there is nothing, virtually there is no change there, nothing happens. So that's called vanishing gradient. So because of this vanishing gradient problems, you adding more layers actually doesn't make sense in traditional neural net because nothing happens down there. So that's vanishing gradient. Second, I'm going to say this advantage of deep learning is feature learning. So in deep learning, it is feature learning, and neural net is called feature engineering. So feature engineering is you have to decide all the important features yourself by hand. So the feature engineering, and in many times this is very, very tricky, very, very complicated. Okay, and you have to decide, which features are very, very important, which are not important, etc. You have to decide all these things by hand, and which is very, very tricky. On the other hand, we have feature learning. So feature learning is done in deep learning. So what's happening in feature learning is we have many layers. In lower level layer, it read the original data, input data, and it automatically extract important features automatically. Okay. And then by using these extracted features in the next higher level, it extracts another higher level features again. Okay, so it's called feature learning. So you don't have to worry about which features are important, which features are not important. You know, deep learning algorithm take care of this, which is huge advantage. Okay, so that's feature learning. That's a big advantage of deep learning. So here, I said it's blessing of dimensionality, and I also mentioned curse of dimensionality. So curse of dimensionalities, I mentioned this in other machine learning methods. So curse of dimensionality is when you increase the number of attributes in input data, actually the number of data you need to train the algorithm grows exponentially. Okay, this is a big problem actually. So in many cases, if you increase the number of attributes, in many cases you don't have enough data to train your method, your algorithm. Okay, so algorithm most likely suffers from overfitting. So that's called the curse of dimensionality. And on the other hand, in deep learning, we have feature learning. So algorithm itself automatically extract important features. So it is kind of reducing the number of dimensions of data. So it automatically reduces the dimension of data. Okay, it's automatic feature learning. So actually you don't have to worry about this curse of dimensionality in theory. So it's called the blessing of dimensionality in deep learning. So you can increase the attribute, but at the same time, you don't have to worry about this number of data, curse of dimensionality. So there's some people call it a blessing of dimensionality. This is huge advantage of using deep learning. So that's one of the reason why many people use deep learning these days. So we're gonna talk about these two issues in this chapter. This slide now explains what's new in deep learning, or what has changed in deep learning. So we have seen the problems of neural net in previous slide, and it was vanishing gradient and feature engineering, and another problem was there are too many parameters in neural net as you increase the number of layers there. So to solve those problems, there are some weapons, there are some techniques to solve those problems. So the first technique we use in deep learning is we train the network layer by layer. Okay, in backpropagation, actually you train entire network using backpropagation. So instead of that, in deep learning, you train network layer by layer. Okay, that's the first difference. And as I said here, you train deep neural net layer by layer. Okay, and because of this, we don't have to worry about this vanishing gradient. So when you train, you simply train one layer only, so you don't have to worry about vanishing gradient. So that's the first technique of deep learning to solve vanishing gradient. Actually, this method is used in RBM and autoencoder. Okay, RBM is restricted Boltzmann machine proposed by Jeffrey Hinton. Anyway, so not all deep learning algorithms use this technique. This technique is used by these two deep learning methods. Second method is sparse connectivity and weight sharing. Sparse connectivity is sometimes called local connectivity and weight sharing. So this one here means in the traditional neural net, so in a hidden layer, you have a certain node in hidden node, and that node is connected to every node in adjacent lower level layer. Okay, so that's called fully connected. So every node is connected to every node in lower level. So that's fully connected in neural net. But in deep learning, it's different. So a node in hidden layer is connected to a small portion of lower level layer. It's called sparse connectivity. It's local connectivity. Okay, and weight sharing is, and we have a node. A node is connected to a small portion of lower level layer, and those weight values are same across all the node in a hidden layer. Okay, that's called weight sharing. So using this sparse connectivity and weight sharing, we can significantly reduce the number of parameters. So even though we have many layers in network, by using this sparse connectivity and weight sharing, the number of parameters significantly reduced. Okay, so that's the second tool we use in deep learning, actually to reduce the number of parameters. And also this technique is very useful to implement feature learning. By using these techniques, we are able to extract important features automatically. Okay. So anyway, this technique is used mainly in CNN deep learning network. So we're going to cover this later in different chapter. Third method used in deep learning is, so in traditional neural net, people use the sigmoid function as an activation function, and later people find out that this sigmoid function actually causes vanishing gradient problems. Okay, so actually a sigmoid function is kind of one of the reasons of vanishing gradient problems. So they come up with many other activation functions that includes ReLU, Linear LU, or many others. Okay, so we're gonna talk about this activation function in a different chapter. So anyway, we have many different activation functions in deep learning. Okay, that's the third tool we use in deep learning. And also we have many different training methods. So they use a gradient descent. So neural net use gradient descent, and deep learning also use gradient descent. But in deep learning we have many variant of gradient descent. So they have many, they improved in the gradient descent in many different ways. So we have many different training methods, including ADAM or RMS prop or NAG, or there are many optimization training methods in deep learning. You're gonna cover this in a different chapter. And another direction of deep learning is adversarial learning. It's called GAN. Okay, generative adversarial network in short. And this is actually, we have two deep learning methods, and they try to maximize each other. Okay, so that's another very popular deep learning method. So we don't go over this one here in this class here. Anyway, this is a very popular one. And in deep learning, again, it has many layers. Okay, because it has many layers, and it doesn't have the vanishing gradient problems, and it actually is able to extract features automatically in a hierarchical way. And that's a big advantage of deep learning. So this is very powerful when you solve very complex problems. There are many other tools used in deep learning. The most popular one is attention in deep learning. There are many others, etc., but we don't cover here in this lecture. So we have seen the differences between neural net and deep learning, also see some techniques used in deep learning. So in the year of 2006, the deep learning paper was published. And this is actually the beginning of deep learning this year. So actually we have three papers. This paper proposed by Jeffrey Hinton. This paper is about the RBM algorithm. RBM means restricted Boltzmann machine. So this is actually the first deep learning paper. And the second one is proposed by Benzio. And this paper is about the autoencoder method. And this one is by LeCun. This one is about CNN method. Actually, this CNN paper was published 1998, and but what happened is not many people pay attention to this paper in this year, and after this paper was published, then people now begin to look at this paper more. So that's what happens. So actually, these three kind of breakthrough of deep learning. Okay. In this chapter, we're going to talk about two things in deep learning. The first one is vanishing gradient problems in neural net. And the second issue is the feature learning, which is advantage of deep learning. So now let's talk about the vanishing gradient problems first. Suppose you have a deep neural net. Deep neural net means neural net with many layers. So in this picture, we have neural net with many layers. In this case, it has only 3 layers, but suppose there are many layers. And in neural net, we train this network using backpropagation method. So let's talk about what is vanishing gradient problem in this network using backpropagation, and why this vanishing gradient problem happens in this network. We use a backpropagation algorithm to train neural net, and backpropagation is actually based on gradient descent method. So in gradient descent method, you define the loss function first, or error function, whatever you call. So you can define loss function using mean square error or entropy, cross entropy, or there are many others. So you can choose one of these and define your loss function. And the goal of learning in gradient descent is you try to find this network weight theta, which minimize this error function. That's the goal of learning in gradient descent, actually in backpropagation. So this is the answer of the goal of learning. So this is error function. Again, this is basically same thing. We change notation from this to this. Okay, make the notation simpler. So anyway, the goal of learning, we try to find this theta value, the network weights, which minimize this error function. That's the goal of learning, okay, in the gradient descent. So now you defined your loss function for the network. And the thing is, actually, the shape of loss function is very complex, very complex like this. It's mainly because your activation function is non-linear and you have many layers. So yeah, because of that, its loss function is very, very complex, not convex, non-concave, etc. So the goal of learning in neural net or deep learning is trying to reach the lowest point, that is error surface. So you want to minimize error. That means you want to reach the lowest point here, lowest point of the function. You want to reach this point, lowest point, from a random initial point. So you begin with a random initial point, wherever, let's say here. And the question is, how do you reach the lowest point here? Okay, that's the question. And the tool we use is we use gradient descent method to reach the lowest point from a random initial point. So you start from here, and using gradient descent, you gradually move to the lowest point. That's the basic idea of gradient descent. This is the basic formula of gradient descent method. So suppose you are in a certain point in the error function, error surface. And again, the goal is to reach the lowest point of error function. So the question is, where do you go? Okay, you are in a certain position here, then you move to where? That is the question. So you have to decide the direction first. Okay, you go in the east or in the west, wherever. Okay, so you to calculate the direction of your next move, you calculate the slope of error function like this. So this determines the direction of your next move. It makes sense. And the second question is, how far do you move? Okay. Then it is determined by this learning rate constant. Okay, this is the step size of your next move. Okay, so that's the basic idea of gradient descent. You are in a certain point in error surface. Okay, your next move is you move in this direction, and you move this far. Okay, that's the basic idea. Okay, so you are in a new position in the error surface, and repeat. So that's the basic idea of gradient descent. Previously, I said neural nets with many layers, like deep learning, suffer from vanishing gradient problem. Then what is vanishing gradient problem, and why this thing happens? By the way, the gradient is the derivative of error function. It's called gradient. So vanishing gradient means, if you look at this picture here, this is a deep neural net. It has output layer, it has input layer. There are many hidden layers in between. So vanishing gradient means, so the gradient value near the top, near the output layer, there's quite values. It's not zero, okay? And but if you move down here near the bottom, near the input layer, the gradient values becomes almost zero. So because the gradient values are almost zero, if you look at the formula of gradient descent, the parameter value never changes because gradient is zero. Okay, 0 times learning constant is 0. So there is actually there is nothing happens. There's no update here. So that's vanishing gradient. So gradient simply disappears, vanishes. That's why we call it vanishing gradient. Then why this thing happens? Why this gradient value becomes 0 down here? That is because this gradient value, when you have many layers, this gradient value actually consists of multiplication of many tiny numbers. So when you calculate the gradient of a certain parameter in a deep network, it actually consists of many multiplications. Okay, and if the each value in the multiplication is very small, the output of multiplication is even smaller, almost zero. That's why we have this gradient value becomes very small, and it causes vanishing gradient problems. So we're going to take a look at, in this next slide, you're going to take a look at more detail of this problem. Yeah, suppose this is one path from input all the way to the output and error function. And in gradient descent, you have to take the derivative of error function with respect to a parameter like theta 1. Okay. Then actually this error function depends on the output value y hat, and this output also depends on the output of hidden layer JL. This is the highest hidden layer, and this also depends on the previous hidden layer value, etc. So all the way down here, this the Z1, the lowest hidden layer, depends on input. So if you wanna take derivative of error function j with respect to theta 1, actually what you have to do is you have to take derivative of j with respect to output first here, okay, because this error function depends on y hat, our output. And then in the next step, you have to differentiate this output with respect to ZL. Okay, so you keep going. So in the middle here, for every hidden layer, you have one term of this, right? So let's say you have 10 hidden layer here, you're gonna have 10 of this. So this is called a chain rule, and so we have many. You can see many multiplications here. Okay, so depending on the number of hidden layer, you're gonna see many of these, and all these terms are multiplied. So so if you look at this formula, if this value is very small, each of this value is small, then you multiply together, then the result of this thing becomes almost zero, right? So that is the problem. That problem is called a vanishing gradient. So this value is almost zero. Okay, so this is used in a gradient descent, and this is almost zero, means virtually there is no update in the parameter. Right, so that's vanishing gradient problem. So each gradient is very small, and this is especially true when you use sigmoid or a tangent hypertangent activation function. We have seen the reason of this in optimization method chapter. So if you're interested in, you can take a look at that chapter. So anyway, that is why do you have vanishing gradient problem when you have many layers in the network. So deep learning network has many layers, and I said in previous slide, neural net with many layers has the vanishing gradient problems. So how do you solve this problem of vanishing gradient? One of the solution is to use some other activation functions. Traditionally, we use the sigmoid or hypertangent. Actually, that causes vanishing gradient problems. So instead of a sigmoid, actually people use a ReLU or leaky ReLU, like some other activation function that helps to solve the that partially solve the problem of vanishing gradient. And another approach to solve the vanishing gradient is explained in this slide. The second approach is you train a deep neural net layer-wise, layer by layer. So the idea is this. So we have a deep neural net with many hidden layers. In traditional backpropagation, so entire network is trained. Okay, you give data and you calculate output error, and based on error and derivative, you update entire network. Okay, that's how you train your network. But in deep learning, in some algorithm of deep learning, they train network layer by layer. So what I mean by that is, you instead of training entire network, you train this part only. This is input, this is output. So training is done between these two layers, okay, not here. This becomes input, this becomes output. So you train this part. So when the training is done, now this layer becomes now input, okay, and now this becomes output. So training is done between this layer, input, output. So keep going. Finally here it is input, output. Okay, training is done. When training is done, now this becomes input to the final output node. So that's how you train this deep neural net layer by layer. Okay, that's one method of solving vanishing gradient problem. This method is used in RBM, a restricted Boltzmann machine, and autoencoder. So these two deep learning methods use this approach. Okay. Some deep learning method, including autoencoder and RBM, train the network in a layer-wise way. So as you can see here in this picture again, we train the network just layer by layer. So in the beginning, we train these layers only. We don't care about the rest for now. So this becomes input, this becomes output. So training is done between these two layers only. So when learning is done here, this layer now becomes input, and this layer becomes output. So training is done between these two layers. So keep going. So at the end, this layer is input and this is output layer. So that's how the training is done in some deep learning method like autoencoder and RBM. Then you may wonder, why do these algorithms use this type of learning? Okay, so is there any advantage of this? Yeah, actually, there's a few advantages of training a network like this. The first advantage is, as I said in previous slide, you can avoid the vanishing gradient problem by training layer by layer. Okay, the gradient in this training is not multiplied by another gradient in this layer. So the vanishing gradient problem doesn't happen here. Okay. And the second advantage of this training is, when you train these layers, usually this picture is a little misleading. The output layer, dimension of output layer here, in this case, this layer is smaller than the dimension of input. So this is a little misleading. So let's say this dimension is 10, it's going to be like 5 or whatever. Okay, so dimension of this one is less than the dimension of input. So because of this, this training, layer-wise training, is very useful in feature learning. So when you train these layers, then from this input, this method actually retrieves some important features as an output here. Okay, and then in next training here, again from these features, it also detects another level of features here in this layer. So so as you move to the higher level, we are able to detect very higher level features of original data. Okay, and at the end, when you make predictions, this output node actually works on these higher level features only. So this whole process is very useful. It actually improves the performance of the network significantly, and that's the advantage of this layer-wise training. So I'm going to add one more thing. So if you look at this deep learning structure, the output is determined by this final layer of final hidden layers, right? And all this process, we have many hidden layers. That's why we call it deep network. So all this process is kind of pre-processing. It's kind of pre-processing to retrieve important higher level features. So you can consider deep learning as this kind of process. So deep learning, the process here is kind of pre-processing. The goal of pre-processing is to retrieve some very important features from original data. Okay, that is kind of a big advantage of using deep learning. Another technique used in deep learning is sparse connectivity, or sometimes called local connectivity, and weight sharing. These techniques are mainly used in CNN deep learning method. CNN. So let's take a look at what these are. In traditional neural net backpropagation, as you can see here, every node here, you take one node here, and this node is connected to every node in lower level layer. So this is connected to every node here, right? And also this node is connected to every node here, etc. Okay. So this connection is called fully connected. Okay. So it's the same thing here. This node is connected to every node in the lower level, and this node is connected to every node here. So this network structure is called fully connected. So this is the way we connect node in a traditional neural net. But as you can see, if you increase the number of layers, the number of parameters, in this case the number of weights here, right? It actually grows exponentially. So let's say you have like a 10 layer or something, the number of parameter is simply hopeless. It's too big. So in deep learning, especially in CNN, they use it use two techniques. The first one is sparse connectivity or local connectivity and weight sharing. So we're gonna talk about these techniques in CNN chapter. There's another chapter of CNN in other lecture. But here in this slide, I'm going to give you a very short introduction, just give you a flavor of what these techniques are. Okay. So sparse connectivity is, if you compare these two pictures, so here this node is connected to every node here, right? But in sparse connectivity, this node is connected to a small portion of low level data. So in this case, it's connected to this 5 of them, right? Again, this is connected to this 5 here. Okay, so each node is connected to only a small portion of lower level layer. Okay, that's sparse connectivity. That's the first technique used in CNN. And second technique is called weight sharing. So weight sharing is, so in sparse connectivity, each node is connected to a small portion of data, okay? And those weight values here, okay, so this node has 5 weight values, right? And these weight values are shared. Shared means their weight value is the same, okay? So these weight values are same across all these nodes, okay? So these weight values are same as these weight values, same here, same here. So that's a weight sharing. So by using these two techniques, actually the CNN can reduce the number of parameters in a big way, okay? So if you compare the number of parameters here and the number of parameters here, you can see the difference. The number of parameters here is significantly lower than the number of parameters in the fully connected case. So that's because of this weight sharing and sparse connectivity, it reduces the number of parameters. And also another advantage is because of these techniques, this technique is very, very effective to extract features from data. So you have seen this feature learning. This is called feature learning, and you have seen the feature learning in previous slide. So in previous slide, feature learning was possible because of layer-wise training, right? So that's the first technique. The first technique of feature learning in previous slide was layer-wise training. And there is another technique for feature learning. In this case here is this sparse connectivity and weight sharing. So because of these two techniques, actually CNN can retrieve important features automatically, and it is called feature learning. So we're going to talk about feature learning in next slide and on. Okay, but here I just give you a very short introduction of these techniques. We have seen so far what the problem of vanishing gradient is and what techniques do we have to solve the problems, etc. And now let's focus on another advantage of deep learning called it's feature learning or feature extraction. Feature engineering is the opposite of feature learning. In feature engineering, it is your responsibility to decide every features in your data. But this job is very difficult, very time-consuming and complex. In addition, you need a lot of domain knowledge to define your data with features. Also, we also need a professional to do all these jobs of defining features. So if you look at this one here, these are set of features used to classify text. So again, you have to come up with all these features for text classification. But again, it is not easy and time consuming. You need a lot of expertise. Another problem of feature engineering is it is not easy to tell which features are important than others. So sometimes some features are actually redundant or not necessary at all. So it is not easy to tell the importance of each features. So that's another problem of feature engineering. This one explains the usefulness of feature learning in deep learning. Previously, I introduced feature engineering where you have to define every features of data, but feature engineering is very time consuming and takes a long time to design, and it's very complex, and also we need a lot of domain knowledge, etc. So it has many drawbacks On the other hand, in deep learning, we have feature learning. So all the features are learned automatically. Okay, so it's very easy to find features. You don't have to worry about it. So deep learning provides a very flexible and effective method to detect these features, detect important features. We have some example of this in CNN and this, the train layer by layer, and this weight sharing, etc. These are very effective tool for feature learning. And because of feature learning, we have what is called the blessing of dimensionality. In other machine learning method, we have something called the curse of dimensionality. I explained this before, but I explain again here. So the curse of dimensionality is in when you increase the number of attribute, then the number of data you need to train the algorithm actually grows very fast, exponentially. So that is curse of dimensionality. So in most cases, you do not have enough data to train your model. So probably you're going to suffer from the overfitting problem. On the other hand, in feature learning is actually a process of reducing dimensions. So in feature learning, even though the original data has a lot of dimension there, actually the feature learning reduces dimension, layer by layer. So near the top layer, near the output layer, the number of dimension is quite small compared to the input dimension. So actually you don't have to worry about this curse of dimensionality. So even though the original dimension is very high, near the output layer, the top level layer, the actual number of feature is quite small. It's a manageable size. Okay, so that's the blessing of dimensionality. That's another advantage of using deep learning. So feature learning is also can be considered as unsupervised learning. Okay, it's kind of pre-processing process of learning. Okay, so it extract features and also it reduces dimensions. Okay, so it is because of this, near the end, near the top layer, near the output layer, because of all this pre-processing, the prediction is quite accurate. Okay, that's the advantage of feature learning. So because of this feature learning, actually, near 2010, this deep learning started outperforming other machine learning techniques in the area of speech and vision and natural language processing. This one shows the example of feature learning, and this is a result of using CNN. So the task is to recognize the car like this. So this one here is the features of lower level hidden layer, and these are the mid-level features in the middle level hidden layer, and this one is the values in higher level layer. So in lower level layer, its features are just low level, very primitive form of features, mostly line or edges, etc. And in the middle level features, by the way, these features are extracted from these features. Okay, so you can think of this as a kind of combination of these features. So this feature here is kind of a middle level features, not very complex, not very primitive. Okay, somewhere in the middle. And near the top, near the high level features, near the output layer, Now this pattern, these features are more complex, very higher level. It's more class related features, right? So you can see as you go up in the layer, the features becomes more complex and class related one. Okay. This one shows another example of feature learning, and here it shows a kind of summary of the difference between feature engineering and the feature learning. So in feature engineering, you have to define every features by hand. So it is difficult, time consuming, brittle, is not scalable in practice. So in feature learning, you don't have to worry about everything is automatic. Algorithm does it for you. So automatically extract important features, and higher level layer represent more meaningful features. So as you can see here, in lower level features, so the features extracted by lower level layers are something like this. So this is the task of classifying human face. Okay, so these features are related to human faces. So in lower level features, these consist of mainly lines and edges. It's a very primitive features of images. And in middle level features, so middle level features basically consist of these, they extract features out of these low level features. So these middle level features are more kind of complex, more abstract. So now these consist of eyes, nose, and ears. It's more human face related. Okay, here in low level features, it's not. It is not human face related. It's more general feature of images in general. So in higher level features near the output layer, and these features are very complex and is very much class related and very abstract. So mostly these consist of face structures. Okay, so finally at the end, the output layer take a look at these, use these features and make decisions. Okay, so that's the advantage of feature learning.